Homework 21, Hypothesis Test for Population Proportion, Video 2. Let's take a look at another example using the critical value approach. A magazine reports that 73% of companies have Twitter accounts. A reporter thinks this number has changed. She surveys 50 companies and finds that 36 of them have Twitter accounts. Can she conclude, it's up with my grammar, can she conclude at a significance level of alpha equals 10% that the number has indeed changed? All right, so let's think about the claim and the counterclaim as we write our hypotheses. Right out the gate, we're claiming that something is equal to 73%. A percent of a population that has a characteristic, in this case, 8% of companies that have Twitter accounts. So that is a claim about P being equal to 73%. Now I could write 73%, but you don't do math with percents. You describe things with percents. You do math with decimals. So what is the reporter counterclaiming? She thinks the number has changed. Now, she didn't say that it went up, and she didn't say that it went down. She said that it's just different. And so her claim is that the population proportion is no longer equal to 0.73. And I'm going to get the evidence to prove it. All right, so there's our hypotheses. Let's find the critical region or regions. Left tail, right tail, or two tail? You should always ask yourself that between here and here. Because the alternative hypothesis has not equals, that means this will be a two-tail test. That means we cut off two tails. And remember, the area of the tails, and more specifically, the area of the critical regions matches the significance level, which means that together, these two add up to 10%. Which means individually they are 5%. So as a decimal, 0.05. And to find the critical values that separate the tails, the critical regions, from the center, the non-rejection region, we would have to go to the z-chart, which means we have to look at our areas as 4 decimal places. But we've already played this game. We've played it multiple times today. Or I have, I don't know when you've watched the videos. Negative 1.65 is the leftmost critical value, and 1.65 is the rightmost critical value. If you do enough confidence intervals and hypothesis tests, you start recognizing that, 5%, 1.65, or 2.5%, 1.96, and things like that. Okay, so now that we have our critical values in our critical regions, remember, the critical regions are the regions in which, if the sample lands there, we reject the null hypothesis. Critical regions. All right, time to calculate the test statistic. And just like in the previous example, we do not have the value of p hat, so we're going to need to calculate it first. Out of the sample of 50 companies, 36 had the characteristic we were looking for, had a Twitter account. So 36 out of 50, as a decimal, that's 0.72. I haven't completed this hypothesis test yet, I kind of made it up. But this is so close to 73%, I get the feeling that this evidence is not sufficient enough to reject the null hypothesis. We got to find our sigma sub p hat. Now remember, that formula uses the value of p from the null hypothesis. A common mistake is to use the p hat. It's not. It's the p from the null. So 0.73 times 1 minus 0.73 over the sample size, which was 50, and then that result will get square rooted. You'd think I'd keep up with the calculator. What up with that silly thing? Calculator, where'd you go? Really? I got to set the calculator down, I can't find it. Oh, here it is. It's hiding behind the book. All right. 0.73 times open parentheses 1 minus 0.73 close parentheses divided by 50 equals, then square root. So to 4 decimal places, 0.0628, which is not our test statistic, but rather the denominator that we need to calculate the test statistic. So the test statistic is start with what your sample gave us, which was 0.72. Subtract what you're claiming in the null hypothesis, 0.73, and divide it by the standard deviation of the sampling distribution of the p-hats, this guy. All right, be very careful. You have to complete the numerator before you divide. 0.72 minus 0.73 equals, now divided by 0.0628, divided by calculator just froze up. Hello? Divided by 0.0628 to 2 decimal places, negative 0.16. Suspicion confirmed. The sample value did deviate from the population claim, but not by much, as evidenced by the fact that its z-score is very small, negative 0.16. So that's just a little bit to the left of 0, and more importantly, it's not far enough to cross negative 1.65. It does not land in the critical region, so we do not reject the null hypothesis. Do not reject the null. And what was the question? Can she conclude that the number is changed? In other words, can she conclude the alternative hypothesis? Well, we didn't reject the null, so we're keeping it and losing the alternative. So the answer to this question is no. But mine was only 72%. So we're blaming the discrepancy not on the fact that this claim is wrong, but just based on the sample that you picked. If you pick another sample, it might be 73%. Actually, out of 50, it was never destined to be 73% exactly, because 36 out of 50 was 72%, but if it were 37, it would be 74%. So it couldn't have even hit 73% with a sample size of 50. All right, so testing a population proportion using the critical value approach, not to sound like a broken record, is exactly the same as testing a population mean, with the one difference of calculating the test statistic. You still set up the hypotheses, the critical regions and critical values, and then once you calculate your test statistic, compare it to your critical values to see if it lands in a critical region. If it does, reject. If it doesn't, do not reject. In the next video, and probably the final video in this series, we'll just do one example looking at a p-value approach. In fact, I think we'll do this example from the p-value approach.